Hi, it's Larry here of Xbox Live's Major Nelson. I'm really excited about this next segment. Joining me is Leo Del Castillo. He is the GM of Xbox Hardware. Now, Leo, we're here in your cool secret lab, but we're going to talk about Project Scorpio, obviously, right?
That's right.
Now, your team builds the hardware.
That's right.
And I'm really excited because earlier this year, you met with Digital Foundry and a few other publications to release details, and you kind of talked about some of the components, but today, we're going to assemble them.
That's right.
So let's go.
And we spent a lot of time talking about the Scorpio engine. The Scorpio engine, right, is the piece of silicon, right? It is an SoC, a system on the chip.
Okay.
It is the most powerful game console SoC made to date.
And that's all right here. I mean, there's millions of transistors, right?
There are 7 billion transistors.
Wow. Okay.
This piece of silicon, 360 square millimeters
Okay.
of silicon on this. There are 15,000 signals coming in and out, or connections for signals coming in and out of this piece of silicon. So the piece of silicon actually has all the circuitry in silicon, right? But we can't make a device out of that just by itself. We have to break those signals out. We have to provide power and clocking. I think that is what I really want to show you, is that you start with a piece of silicon that forms like the heart of your product.
Okay.
But really to make it a product takes a lot of other pieces to come together.
Okay.
So first off, we take that piece of silicon, and first we have to mount on what we call a package. And that package takes those 15,000 signals, interconnects, and breaks it out to something we can manage. So that's 2,400 signals on the back of this package.
Wow.
Now this is the largest package we've ever used. It's a 50 by 50 millimeter package. And this then is the core component for the motherboard.
Okay.
All by itself, it really can't do anything because it needs power, it needs clocks, it needs...
This is the brain.
That's right.
Right?
This is the brain.
And much like me or you or anybody else, if you need the rest of the body to make it happen.
Right. We need a body, we need a recirculatory system, we need all of those things.
Yep.
So that's why I'm going to start walking you through.
Okay, so we're going to start with that.
So the main thing is called the motherboard.
Okay, so that's kind of the skeleton.
That's the skeleton. So we have the SoC, the Scorpio engine is sitting here.
Yep.
And around it we've organized the main part of the memory. So the memory subsystem is 12 gigabytes of memory. We realize that this is the most powerful console ever made. It's going to require a fair bit of memory in order to make it work. The buses are incredible. I mean, you think about it, the signals that go from this chip to this chip travel at the speed of light.
Right.
But they're switching so fast that in the time it takes a bit of information to get from one place to the other, 2 other bits are already on their way.
Right.
And so there's 3 things on that same
I mean,
signal.
we're not even talking milliseconds, we're talking below that.
We're talking picoseconds.
Yeah, picoseconds.
Another key thing that we have to do with the SoC is provide it power.
Okay.
So this SoC can consume a lot of power in order to do its work. We have 15 different voltage regulators that provide different voltages for different parts of the circuit.
Sure.
One of the things that we do is we actually specifically tailor the environment for each specific module.
And that's a new approach in your discipline, is that correct?
Yes, absolutely. What we found is we were trying to drive as much efficiency into the system as possible. 1, because we want to use as little energy as possible.
Sure.
But 2, it also minimizes the amount of heat we have to dissipate. And so if you don't burn it, then you don't have to dissipate it.
Right.
And so driving that efficiency really helps us in those 2 regards.
So for instance, if you only need a gallon of water, instead of walking up and going, well, I'll just take 5 gallons, you only take exactly what you need.
That's right. And so one of the techniques that we've done, we've called it the Hovis method. And one of the things that does is in traditional design methodologies, you would know that each part required a certain voltage range, and you would target that voltage range. But what's built into that is a lot of unknowns around what it's going to look like in the system.
Sure.
So what we do is once it's in the system, we then tailored it to exactly.
So you measure it and say, okay, this is what you said you need, but what do you really need?
That's right. And we measure it, and that actually gets us additional margin that we can then see in efficiencies.
And that's one thing I want to point out is that, people look at something like this and like, oh, I've put together a PC before, this is similar to that. And sure, maybe the components are simple, but those are generic off-the-shelf parts. You have customized every part of this for efficiency, for performance, for the console, correct?
Right, exactly. Do exactly what it needs and to basically be reliable.
And wring out as much power as possible while not wasting any energy.
That's right. So let's start building up the chassis.
All right.
So we use a 2-piece steel chassis.
Okay.
And this is, I'm showing here the motherboard.
Which we just saw.
Which we just saw.
So we just didn't hear.
And added to it is a heat sink, and we're going to come back to that.
Okay.
But this metal pan here is half of the metal chassis.
Yeah.
Now, we use a fairly traditional approach that we started using a few designs back. These are drawn out of solid sheets of steel, and it's a one-piece drawn design with no seams. So
if you flip it over, this entire tray is one piece of metal
Right.
that you create,
this started as a flat piece of metal.
and every console gets one created for it.
That's right. And we form it in a series of punches so that we have a piece that has very precise edges for sealing and has no seams. One of the things that we want to do with this chassis, we want to provide a backbone for the design for one, but it has to provide a lot of other things. For instance, to shield electromagnetic interference.
Because there's a lot of electricity in here,
right.
and there's bits and atoms floating around, and everything's happening, and you need to keep that all inside.
That's right. There's a lot of energy going on inside of here that if we were to let it go out, it would jam your radios and all your wireless
Right.
stuff. And so that has to be contained.
It's got to behave.
It's got to behave. We also have to, provide shielding for the radios. For the radios, they actually have to be working as well.
So it's interesting. A problem you have is like, okay, we have all of the energy in here, which can cause interference, but yeah, we need wireless and we need our controllers to be able to talk to the controllers. So you actually have, I noticed, you mount that outside,
That's right.
outside the container, so it's isolated.
That's right. And we're actually able to utilize the same level of technology that we'd already used in Xbox One S
Okay.
for our Wi-Fi and our accessories radio
Right.
protocols. And so we have two separate radio modules, one for the Wi-Fi, one for the Xbox wireless accessories. I want to talk a little bit about the hard drive.
Yeah.
So one of the things about 4K gaming that we realize is that 4K games are going to require a lot more data.
Yes, they are.
Yeah, higher resolution textures, more of them. And so in order to keep the game loads and game install times reasonable, we knew we needed more performance out of the
Okay.
hard drive. And so we start off with first we have to have the right component, but then we can't just throw that component into the system because how the performance behaves in the system can be influenced by a lot of different things. For hard drives, particularly vibration. Vibration is the enemy of performance for hard drives.
Yep.
And so if you look at the chassis, the mounting system that we use for the hard drive, we have these little rubber dampers
Yep.
that isolate the hard drive itself from the mechanical chassis.
Sure.
And so that provides isolation from anything that might be vibrating, whether it's in the chassis or outside of the chassis.
Right.
Another thing that we do, if you look at the way we do these wires,
You're
here,
actually wiring it in here.
I'm actually wiring it in. And you look at the cable system and you
Yep.
say, here's this plastic cover right here that says
Right.
hard drive on it.
Right.
It's not there just to tell you it's a hard drive cable.
Right.
Actually, the reason for that assembly is to keep the cable itself from touching anything else on the chassis.
Right.
Because vibrations could be coming through that cable to
Sure.
the hard drive itself.
Right.
And so that's the kind of care that we take, so we know that when this thing goes all together, that it's
Yeah.
going to perform in the way that we want it to perform.
Right.
So now, talk a little bit about the heatsink.
Yeah, this is this little guy right here, big guy right here.
This not too small thing that we added to the motherboard, right? As I told you, this is a very high power processor, the Scorpio engine. Matter of fact, it has the highest heat density of any SoC that we've used in previous designs. So this really taxed the thermal system design. We had to basically go to a different level of technology. This is what we went to is we use a technology called a vapor chamber.
Okay.
So vapor chambers are not new, but they've been used in things like servers,
Sure.
high-end systems. But this is the first time we believe that's ever been used in a consumer level product.
Okay.
And we're using this technology because that's what it takes to deliver this kind of performance in a consumer level.
So one of the challenges you have here, we talked about all the energy in here, and energy equals heat, and so on and so forth. But underneath here is where the chip is, and the chip is doing all the heavy lifting. It's doing the thinking, and it's making heat. And you got to get rid of that heat.
That's right. That's a very important. As a matter of fact, it's not just the Scorpio engine, but the memory system itself
Right.
as well. So it
Right.
makes heat. And so what we do, this vapor chamber is actually a copper base. It's hollow inside, but it's filled with deionized water.
Okay.
And then we pull a vacuum on that chamber. So that lowers the boiling point for the water. So now as the water heats up from those electrical components dissipating heat, that turns into steam inside of the assembly.
Right.
And that steam then migrates out and transfers the heat to the base of the
So you guys take care of all. It's not like I have to go. Oh, I got to add water to my radiator. It's all an enclosed system.
Exactly. This is all engineered to last the life of the product.
Right.
That's our goal, is to basically give you a product that you don't have to worry about. You press
Right.
power and you start playing games.
That's amazing.
Now, in order to get that heat then out of the system, we have to motivate that air.
Okay.
So we have
A fan.
a fan, but it's
Yeah.
not just a fan. It's a ducted centrifugal fan. So we start with modeling the system as early as we possibly can, and seeing where the air is going to flow, and we can start working on these designs. So if you look at the ducts and the shrouds and the impellers, so we start with the computational fluid dynamics analysis, and then we start building models.
Okay.
And then those models, we start refining them, and we start measuring and see how they work. And then that finally iterates to the final design that we end up using.
So now you snap this in here, and the goal is that it's going to move air across the vapor chamber, and the warm air is going to exhaust out here.
Right, so we're drawing air through the sides, through the centrifugal fan, then blows it out the back and exhausts the hot air out the back of the chassis. So the next part that we're going to talk about is the source of all that power that we're dissipating.
Yeah.
So obviously we're pulling that power from the wall. One of the things that we did with Xbox One S is we went to an internal power supply, which our customers told us that they loved.
Yes,
and
they're delighted.
We agreed, and so we made sure that we kept that going in future designs.
But to be clear, everybody loves it, but it also the reason it's difficult is because now you're taking something that was outside that may have created power or energy, which is heat, and you moved it inside.
That's right.
So that's a challenge. You just made the challenge a little harder.
Yeah. So not only did we add another piece that we needed to put inside the box, but another part that generates heat, as you said, and impedes airflow. So it does all these things. But how did we react to that? Well, the first thing that we did is we actually built the most efficient power supply we ever made.
Okay.
This level of efficiency we were able to build into this system is much higher because we don't have the extra cabling of the external power supply, and we have shorter connections. And so we put all that thought and energy into this, and it drives the overall efficiency of the system even further. And one of the things that we see here is that we actually take some of the air that comes out of the duct is routed through the power supply itself.
So hey, you're on your way. Go cool off the power supply while
That's
you're at
right.
it.
So it's multi-use.
Right.
So we see
it
that
snaps right in there.
That snaps right in there. And so now let's go to the optical drive.
Yep.
So Xbox One S today is the only game console that is capable of ultra high def Blu-ray playback.
4K HDR.
Until Scorpio.
Beautiful.
Scorpio will now be the second.
Yep.
We just dropped that part
that
right
goes
in
in
there.
there.
So we're able to utilize that technology.
So you can kind of see it coming
straightforward.
together in front of your eyes right here.
That's right. We're starting to fill up that space, and you can see there's not a lot of extra space.
No, there's
left
not.
over.
I mean, it is packed in there.
That's right. Now let's cap it off. So here's the other half of that chassis.
Ah.
I want to spend a little bit of time because in this part you can see it a little bit more closely.
Yeah, look at that.
One would say that forming metal is something that we've been doing for centuries.
Yeah.
Right?
Yeah.
And in fact, I would say punching metal and drawing forms like this in steel punches probably dates back to the Industrial Revolution.
Sure.
But we found places to innovate here as well. One of the things that the chassis needs to do is shield from EMI. So that means you want your holes to be small.
Electromagnetic interference.
That's right, electromagnetic interference.
Okay.
So that means at these frequencies that we generate with these high performance parts are very, very high, and so the holes need to be as small as possible.
Okay.
But at the same time, we're trying to move a lot of air through the system to be able to cool it.
Yeah.
So we want the holes as big as possible.
Right.
So those two things conflict with each other. So one of the areas where that really came really into conflict was in the exhaust area.
Okay.
So we look at this area of the fan. This is where all of the air from the inductive fan has to blow out.
It's got to go out.
We want to maximize the amount of open area there, but we want to keep the hole small enough to be able to shield the system.
Okay.
One of the ways that we did that is we wanted to punch the holes very, very close together.
Okay.
We decided, in fact, to punch them so close together that the material between the holes is thinner than the thickness of the material.
So let me just say, so that little space you see in between the holes is thinner than.
That's right.
Wow.
If you looked at it, it looks like a knife edge this way.
Wow.
And if basically all of the tooling engineers and mechanical engineers that we talked to before we did this said that we shouldn't even try to do this.
Yeah.
It was that hard.
But you guys did it.
But we worked at it.
Yeah.
We have some fantastic tooling engineers, and they love a challenge. And now we have punched holes. These are punched holes, not laser cut holes.
Right.
If you laser cut these, it would be easy.
Sure.
But you can't do that in production very easily.
Sure.
But we actually punch these holes mechanically, and they are perfectly flat and aligned. So
That will go right on top
That will
here.
go-
Notice how there's just not a lot of space in there, and every single millimeter is optimized, and the engineers have to go through here and figure out where to put things, how to put things, how they sit next to each other, how much energy they're creating, any interference. No, you can't. This is extraordinary. You're never going to look at a piece of electronics the same way ever again.
That's right. So now I'll turn it a little bit, and we'll start. And we can now see that this is actually the completed structure.
Yep. And that's the rear. See all the ports
rear,
back
and
there.
you see, I actually have it. I have it right now. I have it upside down for a reason, because I'm now going to start snapping on the,
Now we're gonna put the plastic.
parts that you actually see.
Yep.
So the first step is to put in the bottom, snap it in place, and I will just flip it over here. And we have our top.
Kind of goes down there.
And there you have it.
Slides in. So this is it. This is what people will see.
This is what people will see.
Well, this is Leo. I really appreciate you walking us through. And this is the first look at Scorpio and what it looks like inside and how great it looks outside. And hopefully you'll appreciate a little bit of what Leo and his team have gone through, which has been an extraordinary effort to create the most powerful gaming console ever. Leo, thanks for your time.
Thank you.
Thank you for watching.